Okay, hi everybody. So now we're going to look at a curve in space and also a surface in space. And we have a function that's actually defined on all of space, but the curve is inside of R3 and also the surface. And so any point on the curve, we could plug into the function. Any point on the surface in here, we could plug in. Okay, so let's integrate them. Now first, let's just draw a picture. There's space, and I have some curve going through space. Okay. And then here's another picture of space. And this time I'll draw a sort of interesting looking surface that's in space. Okay. So a curve that I guess I'm calling C, it lives inside of R3, is one-dimensional. A surface, I guess I'm calling it S, it lives inside of R3, is two-dimensional. Okay, and so what is the definition of the integral of f over the curve and the integral of f over the surface? Well, one of them will use one-dimensional volumes, the other will use two-dimensional volumes. And remember, given vectors pointing in space, we can compute the two-dimensional volume of their parallelogram, and we'll use that later. But for now, we'll just do the definition. First thing to do is to split up the curve into pieces that are just, well, line segments for a curve. And then we'll do the same thing for the surface. We'll split it up into parallelograms. You can actually split it up into any pieces whose volume you can compute. And so we know how to compute the volumes of parallelograms, so that's why I'll do that. We could also use, I guess, triangles. We can use a combination of triangles and parallelograms, and this will approximately give us the volume of the surface. This is going to take a while to draw, huh? Let's grab some more points. We'll make some triangles and parallelograms all over this surface. And we'll need to keep going. Right, so underneath there's more pieces. Okay, let's finish up. Almost got it. Okay, so that's the first thing to do. Remember that the integral is going to be a weighted sum where the weights are the volumes of little pieces. And then we take, well, now we need points. So let's choose some points. I'll put those in pink. Choose a point on each piece. Okay, and those are like the xi are the points. And over here, we also have to choose a point on every piece because we need to evaluate the function. And then we're going to just take the volume of this piece times the value of the function right there. And we'll keep doing that and add it all up. Okay, so first, part A. What is the definition of this? Well, the integral of the function f over the curve C is equal to, well, it's equal to a limit of the volumes of pieces of the curve times the value of the function at some point on that piece. We're going to take a limit as the volume of the pieces goes to 0. Okay. It's very, very similar. In fact, identical for a surface. Now these volumes, this is a two-dimensional volume. So maybe I better say that. Volume of the piece SI times the value of the function. And oh, I forgot the limit. So let's put limit as the volume of the SIs go to 0. Okay, so I have to make some comments. I'll make those in words. First, I'll say that this is a one-dimensional volume of the piece labeled CI. I mean, we're going to have C1, C2, C3, C4, etc. And so I've referred to them all as the CI. I is for index. It's just a dummy variable to label all the pieces at once. Makes it easier to talk about it. Then what's this? Well, this is the value of f at some point xi that is on the ith piece of the curve. In exactly the same way, this will be the two-dimensional volume of the piece SI, and this is the value of f at some point on that ith piece. Okay. And then I'll just say, for a blanket statement for both of these, is the limit, the limiting value of these weighted sums, well, limiting as what? As the limit as the piece, the size, or the size of the pieces goes to 0. The limiting value of these weighted sums as the size of the pieces goes to 0 is the integral. Okay? These weighted sums, well, they're weighting the value of f times the volume, and so that's why we have, the volume of this object and the function f. And I think this looks pretty good. Yeah. Okay, so that is the definition. The definition is really this formula here and this formula here. But those formulas have this picture and this picture. And I had to label some of the formulas because I need to make it clear that I'm talking about one-dimensional pieces. Even though we're sitting here in three-dimensional space, if we're integrating over a curve, the curve's volumes should be one-dimensional pieces. If we're integrating over a surface, the volumes should be two-dimensional volumes, okay? And remember, the square root of the determinant of the Gram matrix, this is how we're going to actually compute these numbers, is we're going to use this formula to get volumes of different pieces of surfaces and curves and higher dimensional objects, okay? So this whole thing can be used to integrate sort of any manifold m and any function, even if m is a subset of r to the n, and m is, 7-dimensional. We could take this to be r to the 100. Okay. For example, m could, maybe if you want to look up Wikipedia, Calabi-Yau manifold. Look this up. We could take m to be one of these. It would be a 6-dimensional thing. And then we could try to integrate over it and try to figure out how many holes it has. But okay, that's for later.